In 1935, Sir William Stanier staked his reputation on the most radical locomotive Britain had ever seen. It was a 2,400 horsepower turbine engine with no pistons, no cylinders, and no equal on British rails. It was faster, smoother, and more efficient than anything running. It should have changed everything, but one fatal flaw, buried in the physics of the turbine itself, would destroy not just this machine, but an entire vision of the future. And that flaw was not about what the turbomotive could do. It was about the one ordinary thing it could not do. William Stanier arrived at the London, Midland, and Scottish Railway in 1932 with a reputation for boldness. He came from the Great Western Railway, where his designs had already challenged the old order. Now, with the LMS desperate to close the gap with the LNER's record-breaking Pacifics, Stanier was handed something rare in British industry: total freedom. The board gave him a blank slate to modernize the locomotive fleet. For Stanier, speed was never just a number, it was proof of progress, a public spectacle, and a personal mission. He believed the future belonged to high output, high-speed engines, and he was determined to drag the LMS out of its past. The stakes were more than technical. The LNER's Mallard was making headlines, and every mile per hour was a matter of corporate pride. Stanier saw the turbine not as a gamble, but as a calculated answer to this challenge, a machine that could deliver smooth, continuous power and run faster, with less wear, than anything built before. In private memos, he argued that turbine propulsion would bring a new era of efficiency and prestige to British rail. He pressed the case in the boardroom and won. By 1935, the project had official backing, with the promise of a new flagship that would outpace the competition and redefine what steam could do. Stanier's ambition was not reckless. He studied the Swedish Ljungström turbines, consulted with marine engineers, and demanded that every detail serve his vision for speed and power. He insisted on a design that would eliminate the hammer blow of reciprocating engines, reduce maintenance, and showcase the LMS as a leader in railway innovation. The turbomotive would be a symbol, one that could not be ignored by rivals or the press. This was not the work of a committee. Stanier's signature appeared on every major decision, from the selection of the turbine supplier to the final design brief. He pushed for a 6-nozzle steam admission system, a radical departure from the norm, to keep the turbine running at its most efficient speed. He overruled doubters, convinced the board to invest in new tooling, and reserved crew's best engineers for the project. His confidence was infectious, and for a moment, it seemed that nothing could stand in the way of the turbomotive's promise. But ambition is a double-edged sword. Stanier's drive to leap ahead would soon meet the limits of physics and the realities of railway life. The flaw that would doom the turbomotive was already written into its blueprints, a flaw that no amount of vision or authority could erase. The decision to build the turbomotive did not rest on one man's ambition alone. Inside the boardroom at Euston, the LMS directors gathered in the summer of 1935 to weigh Stanier's proposal. The minutes from that meeting record a rare moment of unity. Every director present voted in favor of the project. The official resolution authorized a dedicated budget. £160,000 was set aside, not just for the locomotive itself, but for a complete overhaul of the crew works. Specialized tooling was ordered, and a new turbine section was established within the workshops. These were not half measures. The board's signatures committed the company to a path that would consume resources, manpower, and a slice of the railway's reputation. Crew's engineers found themselves at the center of an experiment that was as much about pride as it was about progress. The tooling ledgers from late 1935 show line items for custom gear-cutting machines, high-speed lathes, and new metallurgical furnaces, each one a direct response to the demands of turbine technology. The turbine section was given autonomy over its schedule and budget, answering directly to Stanier and the board. Monthly reports flowed from Crewe to Euston, detailing every challenge and every breakthrough. For the men on the shop floor, this was a break from routine, the old patterns of piston and rod replaced by the unfamiliar logic of vanes, rotors, and reduction gears. The board's gamble extended beyond money. By earmarking workshop space and skilled labor for the turbomotive, they diverted resources from proven designs at a time when the LMS could ill afford mistakes. The directors understood the risk. Internal correspondence reveals heated debates about the wisdom of betting so heavily on a single prototype. Yet the promise of leapfrogging the LNER and of securing headlines for British engineering proved irresistible. The board minutes, now preserved at the National Archives, carry the unmistakable tone of confidence. The turbomotive would be the LMS answer to Mallard, a machine to silence rivals and critics alike. With formal approval granted, the gears of the institution turned. Purchase orders were signed, overtime was authorized, and the first steel for the turbine's casing was rolled at Crewe before the year was out. The company's resources were now locked to Stanier's vision. There would be no turning back, no easy retreat if the experiment failed. The fate of the turbomotive was sealed not just by engineering, but by a boardroom's collective will, a commitment that would soon collide with the realities of the railway and the flaw waiting in the heart of the design. Inside the newly outfitted turbine section at Crewe, the engineering team set out to build a machine that would outpace every piston engine in Britain. At the heart of their ambition stood a single, gleaming rotor, an axial flow steam turbine designed to spin at 7,000 revolutions per minute. This was not the slow pounding motion of pistons and rods, but a seamless rush of power channeled through vanes and blades cut from high-grade steel. The turbine was rated at 2,400 horsepower, but its real promise lay in smoothness. No hammer blow, no judder, just an unbroken surge of torque from boiler to rail. Delivering that force to the wheels required more than brute strength. The engineers devised a two-stage reduction gearbox, cut with helical teeth and hardened to 55 on the Rockwell scale. This gearbox, with its 14-to-1 ratio, transformed the turbine's frantic speed into the measured rotation of the locomotive's driving axle. The high-speed pinion meshed with a split-case gear, each tooth oiled by a pump driven from the turbine's own rear bearing. There was no clutch, no disengagement. The turbine was always in play, and every change in speed or load rippled instantly through the mechanism. Steam entered the turbine through a set of 6 independently controlled nozzles, a system borrowed from marine engineering, but refined for rail. Instead of throttling back and sapping efficiency, the driver could select how many nozzles to open, keeping the turbine spinning close to its optimal speed, even as the train accelerated or slowed. The boiler, built for 150 pounds per square inch and a mass flow of 25 kilograms per second, fed the turbine a continuous stream of superheated vapor, which expanded through 12 bladed stages before roaring out the exhaust stack. The exhaust temperature soared to 350 degrees Celsius, demanding robust lubrication and relentless attention to bearing health. The entire drive system was a study in precision and risk. With no conventional reversing gear, the main turbine could only push forward. Every component, from the bladed rotor to the oil pump, was designed for a single direction. Crewe's best fitters and machinists spent months fine-tuning clearances and checking tolerances, aware that any misstep at these speeds could shatter steel or seize a bearing in seconds. Yet in the glow of new machinery and the thrill of technical conquest, the limitations were easy to overlook. The turbomotive, on paper, was a masterpiece of modern engineering, a locomotive that seemed destined to sweep aside the old order. But beneath the polished casing, the seeds of disaster had already been sown. The turbine's promise, smooth, relentless forward power, came with a hidden cost that no amount of optimism could erase. Turbines, by their nature, are creatures of one-way motion. In the turbomotive, the main turbine was engineered to drive forward only, its blades and steam passages shaped for a single, efficient flow. The laws of physics did not bend for ambition. Reversing a turbine meant fighting its own design, and the result was catastrophic inefficiency. Stanier's team, pressed by operational reality, resorted to a workaround. Deep inside the locomotive's frame, they installed a second, much smaller turbine, dedicated solely to reverse. Workshop records from crew show the auxiliary unit rated at just 400 horsepower, a fraction of the 2,400 delivered in forward motion. Test logs reveal the limits immediately. On a level track, the reverse turbine could barely push the engine above 20 miles per hour. Any steeper grade or heavier load, and the locomotive stalled. The numbers were undeniable. Reverse running was not just slow, it was powerless. Crews described the experience in blunt terms. The driver, faced with a siding or a blocked main line, would grip the reverse lever and wait for the lag as steam choked through the smaller turbine. The response was sluggish. The locomotive hesitated, and the cab would fill with the uneasy whine of machinery, straining against its own constraints. Firemen reported oil pressure dropping dangerously low during these maneuvers, with bearing temperatures spiking as the lubrication system struggled to keep up at low speeds. Maintenance diaries from 1937 document repeated bearing seizures and cracked gear casings, all traced back to the stresses of reverse operation. Stanier's engineers had hoped that clever design could mask the flaw. They experimented with revised throttle linkages, tweaked the steam admission, even proposed a double-stage reverse turbine. Nothing changed the basic fact: the turbomotive could not reverse with any real authority. Every timetable, every yard movement, every operational plan had to account for this one-way trap. In the boardroom, the flaw was still spoken of as a manageable inconvenience. On the rails, it was an ever-present liability, a weakness that no amount of prestige or technical brilliance could hide. Depot foremen watched the turbomotive's promise unravel day by day. Each morning brought a new set of handwritten memos, delays at Edge Hill, shunting headaches at crew, a backlog of engines waiting for the turntable. The reverse turbine's weakness turned routine movements into logistical puzzles. Instead of gliding through the yard, the turbomotive stalled in sidings, unable to back up with any authority. When a main line was blocked or a platform change was called for, crews had to summon a pilot engine just to nudge the turbine backwards. These pilot moves, once rare, became a grudging part of the daily schedule. The cost was measured in minutes lost, coal burned, and tempers frayed. Maintenance logs from 1937 record a sharp rise in unscheduled shop visits. Bearings overheated during slow-speed reversals, oil pressure dropped off, and gearboxes whined under the strain. The depot's repair crews worked overtime, swapping out cracked cases and seized bearings with a frequency that alarmed the accountants. The turbomotive's high-speed bearings, designed for relentless forward motion, simply could not cope with the start-stop rhythm of real railway life. Station masters complained of the locomotive hogging scarce turntables, blocking access for other engines. On busy days, the turbomotive's need to be turned or piloted by another locomotive threw off the entire marshalling yard's rhythm. A single missed slot could cascade through the timetable, forcing delays that rippled down the line. The official running books show the turbomotive's average depot dwell time creeping higher than any other Pacific in the fleet. Steam penalty figures circulated among the foremen, a 30% increase in coal use for reverse shunting, estimated from the boiler logs. While those numbers were debated, the effect was felt in every ton of coal shoveled and every hour spent idling on a siding. The locomotive that was supposed to save money and time instead drained both. By 1938, depot managers began to question whether the turbomotive was worth the trouble. Each disruption, each costly repair, pushed the boardroom closer to a reckoning. The flaw was no longer theoretical. It was written into the daily rhythm of the railway itself. The turbomotive's promise faded under the weight of its own numbers. By the late 1940s, the LMS Finance Committee faced a stack of reports that cut through the optimism. Maintenance charts from crew told a blunt story. For every 1,000 miles the turbomotive ran, it spent nearly twice as many hours in the shop as a conventional Pacific. The high-speed bearings, the reduction gearbox, and the specialized oil pumps each demanded constant maintenance. The turbine's complex internals meant even routine inspections dragged on for days, while spare parts had to be machined from scratch. A standard Princess Royal could expect 12,000 miles between overhauls. The turbomotive rarely reached 4,000 before being sidelined for gearbox work or bearing replacement. Annual repair bills climbed to 12,500 pounds, the costs dwarfing the modest coal savings Stanier once promised. The CME's own cost memo, circulated in 1948, warned that even the best-case savings in fuel and track wear could not offset the relentless drain of shop hours and specialized labor. The Finance Committee, once seduced by the dream of turbine efficiency, now saw only red ink. Line graphs plotted on boardroom easels showed the turbomotive service miles falling as costs soared. Each unscheduled repair meant lost revenue, overtime wages, and a ripple of delays across the network. In the end, the numbers left little room for sentiment. The directors faced a simple calculus. The locomotive that was built to outpace its rivals had become a burden the company could no longer afford. The boardroom's reckoning arrived in the form of a formal vote. There was no room left for hope or half measures. Faced with mounting costs and a locomotive that could not fulfill its promise, the directors authorized the turbomotive's conversion at Crewe. The order, signed off in 1949, called for the turbine to be stripped out and the frame rebuilt as a conventional four-cylinder express engine. Workshop logs from Crewe captured the scale of the task. The turbine, the reduction gearbox, and all associated pipework were removed, leaving only the Princess Royal chassis as a foundation. Over the next 3 years, the rebuild team worked through a catalog of modifications. New cylinders were cast, valve gear installed, and the boiler adapted to suit the familiar rhythm of piston power. The process was methodical but heavy with resignation. For the engineers who had once assembled the turbine's delicate vanes and precision gears, the conversion was an admission of defeat. Crewe records from 1952 list the locomotive under a new identity, BR 46202, Princess Anne. The transformation was complete, but the spirit of the turbomotive, its radical promise, and its fatal flaw remained locked in the memories of those who built and rebuilt it. The experiment was over. What emerged from the works was no longer a symbol of the future, but a return to the safety of proven ground. The turbine's ambition had been written out, replaced by the steady certainty of pistons and rods. In the end, the only thing left of Stanier's vision was the number on the cab and the lessons learned from a gamble that failed to pay. Ambition built the turbomotive, and hubris destroyed it. Stanier's vision promised a new era, but one overlooked flaw ended the revolution before it began. Today, as industries bet billions on untested innovation, the cost of a single blind spot grows ever higher. Progress demands boldness, and history punishes arrogance. The line between genius and disaster is always thinner than it seems. Share your thoughts on technological risks below.